Right now, between Mars and the Sun, an object from another star system is doing something never recorded before. It looks as if it just hit the brakes. First, it grew a jet of material blasting forward into its direction of travel. Then that jet flipped. A comet tail began streaming behind it, a pattern no comet is supposed to show. If this is natural, comet physics has a hole in it. If it is not natural, we may be watching first contact. To follow this story as it unfolds, tap like, subscribe, and keep listening. The object has a name that sounds like something out of a science fiction novel, 3I Atlas. It is roughly the size of Manhattan, a frozen mountain of rock and ice and metal that does not belong to our solar system at all. For billions of years it drifted through deep interstellar space, dark and silent. Now it has wandered into the inner regions of our system and, right in front of us, it appears to have changed the way it moves. 3I Atlas is only the third confirmed interstellar visitor humanity has ever seen. The first was Oumuamua in 2017. The second was Comet Borisov in 2019. Both came and went before most people had even heard their names. 3I Atlas is different. It arrived in an era of all sky survey telescopes and hungry astronomers who have been waiting for another chance. From the moment it was spotted, almost every instrument that could see it was turned in its direction. That is where the story becomes difficult to dismiss. This is not a fuzzy light on a single camera. The Nordic Optical Telescope in the Canary Islands has photographed it in fine detail. The Gemini South Telescope in Chile has captured deep images of its growing coma and tail. A high-resolution camera aboard a Mars orbiter has already taken the sharpest pictures ever obtained of an interstellar object as it swept about 12 million miles past the red planet. This thing is under constant surveillance. As those images and spectra came in, one detail stood out. At first, the dust and gas were not being blown backward away from the sun, the way every astronomy textbook says they should. Instead, a bright plume seemed to project forward into the direction of motion, like a flashlight beam pinned to the nose of the comet. Astronomers call that a forward-pointing tail, or anti-tail, and under rare conditions, natural comets can show something that looks a bit like it. But in this case, the shape, the timing, and the composition raised eyebrows. Then came the flip. After weeks in which the forward plume dominated, new images showed something much more familiar. A pale ribbon of dust and gas streaming out behind 3I Atlas. Stretching away from the Sunday, the anti-tail faded. The normal tail took over. On paper, that sounds like a technical detail. In practice, it looks unsettlingly like a sequence. First, a plume that opposes the motion, then a long streaming wake that follows it. One Harvard astrophysicist looked at that pattern and dared to say the quiet thought out loud. If you wanted to slow down a spacecraft that was barreling into a new solar system at interstellar speeds, you would fire your engines into the direction of travel. Your exhaust would blast forward, forming something like an anti-tail. Once you had shed enough speed, you would rotate the vehicle. The exhaust and the strip material would then trail behind, looking exactly like a conventional tail. The idea is outrageous, yet the data stubbornly align with it. We are watching an object that does not belong to our sun at a distance where only a handful of probes have ever flown, and its behavior lines up uncannily well with a braking maneuver followed by reorientation. If any other machine did this in front of you, you would not hesitate to call it controlled. Because this machine is wrapped in ice and dust and it comes from another star, we hesitate. None of this means 3I Atlas must be artificial. Space has a way of humbling our imagination. Comets are notoriously messy. Their surfaces crack and spin and erupt in ways that even experienced comet specialists sometimes struggle to explain. Under the right geometry, sunlight can sculpt dust into shapes that trick the eye. Gas jets can point in unexpected directions. More than once, science has had to back away from dramatic claims when more data arrived. Yet for 3I Atlas, the more data we gather, the stranger it looks. The forward plume that should have been rare and marginal became dominant for weeks. The transition to a regular tail happened at a very specific distance from the sun, as if some threshold had been crossed. The amount and type of material streaming away from the object do not match what you would casually expect from a normal comet. That is why the phrase controlled maneuver has entered serious scientific conversation, not in late-night talk shows, but in research papers and observatory planning meetings. There is another twist. While this drama plays out between Mars and the Sun, most of the planet has no idea it is happening. News feeds are full of politics and celebrity scandals, while, just over 100 million miles away, an object older than our solar system may be changing its speed in a way we cannot fully explain. A network of telescopes is watching every move. A handful of researchers are arguing about what it all means. The rest of us are left with a simple question. How did this visitor arrive here, and why is it behaving as if someone is driving it? When astronomers first spotted this object, nothing about it looked revolutionary. It began, as many cosmic stories do, with a faint smudge in a routine survey image. On an early July night, the Atlas Survey telescope in Chile registered a dim point of light that shifted ever so slightly between exposures, just bright enough to be real, and just strange enough to be worth a second look. Atlas is designed to find things that move: asteroids, comets, potential impact threats. This seemed at first like just another one of those. The software flagged the moving point and passed it to human eyes. Astronomers did what they always do. They measured its position against the background stars, fed those coordinates into orbital calculators, and tried to fit a path around the Sunday. Most new objects settle quickly into an ellipse, a stretched circle that tells you it belongs to our solar system. This one did not want to behave. The more data points they added, the worse the usual solutions fit. The numbers refused to bend into a closed loop. After a few nights, a pattern emerged that made everyone sit up. The curve that best matched the data was not an ellipse at all. It was a hyperbola, the mathematical signature of an interstellar traveler. This trajectory does not circle the Sunday. It dives in from far away, swings around once, and then heads back out into the galaxy, never to return. Suddenly, that faint Atlas dot was no longer a local curiosity. It was a visitor from another star system racing into our midst. The next question was speed. How fast was this thing moving as it fell toward the Sunday? The answer came out to roughly 210,000 kilometers per hour relative to our star. That is fast enough to cross the width of the United States in about a minute. For an interstellar object, it is quick but not absurd. It fits comfortably into the range you would expect for something that has spent billions of years drifting through the galactic gravitational field. In other words, nothing about the velocity alone screamed artificial. What did scream something else was its age. By tracing its path backward through space and comparing its composition to models of early galaxy chemistry, astronomers arrived at a staggeringly old birth date. 3I Atlas appears to have formed between 7 and 10 billion years ago, long before the Sun lit up, back when the Milky Way itself was still a restless young disk, thick with gas and newborn stars. Our entire solar system is only about 4.5 billion years old. This object has been around nearly twice as long. Try to hold that in your mind for a second. When 3I Atlas formed, the Earth did not exist. The Sun did not exist. The clouds of gas that would one day collapse into our system had not yet cooled. Somewhere out in the galaxy, in a star system that may have since died, something assembled this body. Maybe it coalesced in a distant comet belt. Maybe it was thrown out by gravitational chaos around giant planets. Or, in the bolder reading, maybe it was built, then it left, or was flung, and has been wandering ever since. Over those unthinkable spans of time, it would have crossed vast stretches of interstellar space, gently curved by the pull of passing stars, nudged by molecular clouds, bathed in cosmic rays. Every so often it might have skimmed through another planetary system, briefly warmed, then sent, back into the dark. Most of that journey would have been uneventful. No one watching, no one caring, until now, when its path happened to line up with a tiny blue world full of curious apes with telescopes. The moment astronomers realized 3I Atlas was on a hyperbolic trajectory, phone lines and email threads lit up. Observatory time is precious, but suddenly everyone wanted a piece of this target. Within weeks, it was being tracked not just by Atlas, but by observatories around the world. Northern and southern hemisphere telescopes took turns as the Earth rotated. Proposals were written overnight to point big instruments at the newcomer, to squeeze in observations any time it rose above the horizon. At first, the excitement was simple. This was only the third interstellar object ever confirmed. Oumuamua had given us a fleeting, frustrating glimpse of something that broke a few rules and then vanished. Borisov had reassured us with a more ordinary comet-like behavior. 3i, Atlas promised a much better look. Its orbit kept it in view for months instead of weeks. Its brightness was high enough that a wide range of telescopes could follow it as it approached the Sunday. For once, we had time to prepare, to plan, to gather a rich data set, yet baked into that optimism was a subtle unease. This object is older than any planet in our system, forged in conditions we can only dimly reconstruct. Its very presence here is a statistical fluke. The galaxy is enormous, and yet this ancient wanderer just happens to pass close enough for our telescopes to catch it at the exact moment in history when we have the technology to notice. That coincidence alone makes the hair on the back of the neck stir. When the first detailed observations started showing behavior that did not match expectations, that unease thickened into something else. If 3i Atlas were merely a strange fossil comet from a lost star, its story would already be astonishing. It would be a message in a bottle thrown into the galactic ocean billions of years ago, washing up now on the shore of our awareness. The fact that, once inside our system, it began to act like a vehicle that can adjust its own motion lifts that story into another category entirely. The way we found it is pure astronomy. The way it is behaving is what turns that astronomy into a mystery. When telescopes first caught the strange forward-pointing plume on 3i Atlas, many astronomers tried not to overreact. Comets are chaotic things. They spin, they crack, they throw out gas and dust in complex patterns. Under certain alignments, a comet can appear to sprout a stubby spike that seems to point toward the sun or even a little ahead of its motion. You can usually fix that illusion with geometry and a calm explanation. For a little while, that is exactly what people tried to do. In the images from the Nordic Optical Telescope, though, this feature refused to look like a harmless quirk. The plume was not a faint smudge or a minor side effect. It was bright and well-defined, projecting forward into the direction of travel like the wake of a boat turned around. Instead of a long tail streaming away from the sun, the material seemed to cluster along the path that 3i Atlas was ploughing through space. It was as if something on the object was deliberately throwing mass into the oncoming wind. Light alone cannot tell you everything. To understand what is actually being thrown off, you need spectra. When light from the plume is split into its component colors, specific atoms and molecules leave telltale fingerprints. For comets, those fingerprints are familiar. Water vapor reveals itself through certain bands in the ultraviolet. Carbon dioxide and carbon monoxide paint features in the infrared. Cyanide, a common though unsettling comet ingredient, glows in the visible range. 3i Atlas had all of these in abundance. So far, so comet-like. Then there was the outlier. Mixed into the spectral data from the forward plume was evidence of a nickel-rich alloy with a ratio of nickel to iron that does not match any known natural mixture. On Earth, metallurgists create such blends on purpose. They tailor nickel and iron and other elements into high-performance alloys for turbines, spacecraft structures, and extreme environments. The specific pattern of lines seen in the data from 3i Atlas lined up far better with human-engineered metals than with the simpler alloys found in meteorites and planetary cores. That is the moment the room gets quiet. A natural object can certainly contain nickel and iron. Many asteroids are literally made of the stuff. There are even natural nickel-iron alloys. But the detailed proportions matter. Think of it like a recipe. Nature throws ingredients together in broad strokes. Human technology refines and tunes them into precise combinations that perform specific jobs. In the spectrum of 3i Atlas, the recipe looked strangely familiar, as if someone or something had mixed it with intent. The cautious response is to ask whether some exotic natural process in a distant star system could mimic that recipe. Perhaps in the early, metal-poor galaxy, certain cooling rates and pressures in a protoplanetary disk could freeze out alloys we do not see in our own neighborhood. Perhaps repeated heating and cooling in interstellar space could segregate metals in unexpected ways. Teams have already started running computer models to see whether any plausible scenario can produce the blend inferred from the plume. It is not impossible. But so far, every natural explanation has to work very hard. Now place that alloy back into its physical context. It is not quietly buried deep inside a rocky core. It is being expelled in a directed plume that points along the direction of motion, exactly where a braking engine would throw its exhaust. You have forward thrust, and that thrust is laced with a material that looks engineered. If any rocket on Earth behaved this way, no one would hesitate to call it a propulsion system. The only reason we hesitate here is that admitting that possibility means acknowledging technology older than our Sunday. Of course, there are counterarguments. Spectral data are messy. Telescopes must subtract the glow of the comet coma, the background sky, the noise of instruments. Subtle errors can masquerade as exotic compounds. Some researchers urge patience. They want more observations from different angles, independent analyses, and better calibration before they will concede that the nickel alloy really is as weird as it appears. Given how extraordinary the implications are, that skepticism is healthy. Yet the pattern is hard to ignore. The plume is forward-facing when the object is farther from the Sunday. It is compositionally distinct, rich in carbon dioxide, cyanide, and this unsettling metal signature. Then, as 3I Atlas draws closer, and the radiation, pressure climbs, the forward plume wanes. A classic tail blossoms behind it. The metal-rich exhaust seems to shut down just as solar heating is capable of driving a more conventional cometary show. It is as if one system hands off to another. Individually, each element of this story could be excused. A forward plume can be blamed on an odd rotation state and tricky viewing geometry. A strange alloy can be waved away as a misread spectrum or an unknown natural process. A transition from one type of activity to another can be chalked up to changing sunlight. But when all three line up in sequence, the mind keeps circling back to a simpler picture. A massive object from another star, carrying engineered metal, first expels material forward, as if braking, then reorients and lets natural outgassing take over. The universe does not owe us simplicity. Sometimes the truth really is a stack of unlikely coincidences. The unsettling possibility with 3I Atlas is that the less convoluted explanation, the one with fewer contortions, is also the one that forces us to admit we might be watching a machine. And if that is even on the table, then every new spectrum and every fresh image is not just data about a comet, it is potential evidence about whether we are alone. To understand why astronomers are losing sleep over 3I Atlas, you have to picture what happened in slow motion. Out beyond the orbit of Mars, the object is falling toward the Sun along its hyperbolic path. At those distances, comets usually begin to stir but not erupt. Maybe a faint coma appears, a soft halo of gas and dust. A thin tail may start to grow, pushed gently away from the Sunday. That is the script written in every textbook. 3I Atlas did not follow that script. While it was still far from the Sun, around 2 to 3 times the distance between Earth and our star, the dominant feature was that stubborn forward plume. Material was not being swept backward as you might expect. Instead, most of the visible dust and gas seemed concentrated along the direction of motion, like a torch beam pinned to the nose of the object. As the days passed and the visitor fell inward, that plume held steady. Meanwhile, the solar energy bathing it was ramping up. The intensity of sunlight grows rapidly as you move closer to the Sunday. At twice Earth distance, the radiation is already about 1/4 of what we feel here. At 1.5 times Earth distance, it is nearly half. For a fragile interstellar ice ball, that is an increasingly harsh environment. More and more frozen gases should be sublimating from its surface, feeding a tail that is pushed back by the constant wind of photons streaming from the Sunday. That is exactly when the flip occurred. In September, images from the Nordic Optical Telescope showed that the forward plume was fading and a much more conventional tail was taking over. Dust and gas were now noticeably trailing behind 3I Atlas, stretched away from the Sun like a banner in a strong wind. The anti-tail, once the star of the show, became a supporting feature and then nearly vanished. It looked less like a random fluctuation and more like a handoff from one mode of behavior to another. If you strip away the scientific jargon, the pattern is almost disarmingly simple. Stage 1, a forward-pointing exhaust. Stage 2, a trailing wake. That is where the spacecraft analogy stops being a cute metaphor and starts to feel uncomfortably literal. Imagine you are piloting a vehicle that has spent billions of years in interstellar space. It is falling toward a new star system at high speed. You want to slow down enough to take a closer look without slingshotting straight through. The most efficient way to reduce your speed is to fire your engines against your direction of motion. Your exhaust would stream out in front of you in the exact direction your craft is moving. To a distant observer, that would look like a forward-pointing jet. The craft would shed kinetic energy as it pushes against its own motion, trading speed for heat in the exhaust. Once it has slowed enough, you would rotate the vehicle. Either you shut down the main engines and let natural forces take over, or you switch to a different propulsion mode. In either case, the material that continues to escape your hull would now trail behind you. Seen through that lens, the anti-tail-to-tail transition is not a vague curiosity. It is the textbook signature of a braking maneuver, followed by reorientation. The timing makes sense as well. You would not want to be firing large engines when you are very close to the sun, where intense radiation and thermal stress could damage your systems. You would complete the main braking burn farther out, at a safer distance, then let gravity and residual outgassing carry you through the inner system. Natural explanations do exist, and they deserve to be heard. Some comet specialists point out that an anti-tail can appear when the geometry between the comet, the sun, and the Earth is just right. Dust can spread out in a thin sheet along the orbital plane. From our point of view, that sheet can project ahead of the nucleus, creating what looks like a forward spike, even though the dust is really trailing behind in three-dimensional space. As the object moves, and our viewing angle changes, that configuration can disappear, and a normal tail can take over. This geometric trick has been seen in a few rare comets before. It is not science fiction. The question is whether that explanation truly fits what we are watching now. In those earlier cases, the anti-tail was usually a delicate, transient feature. With 3i Atlas, the forward plume was bright, long-lived, and aligned in a way that does not perfectly match the textbook anti-tail geometry. It also carried that unusual nickel alloy signature, which is very hard to fold into a simple dust sheet story. There is also the matter of pacing. The shift from anti-tail dominance to classic tail growth happened over a relatively narrow band of distance from the sun, roughly as 3i Atlas crossed the region where carbon dioxide sublimation gives way to strong water-driven activity. That change in energy input would naturally alter the pattern of outgassing. It could, in principle, flip the apparent direction of dust structures without any alien engineering. But if that is the case, we are still left with a comet that chooses the one geometry that mimics a braking burn for weeks on end, then switches states just when an engineer might choose to shut engines down. From a distance, the whole situation feels like a cosmic Rorschach test. If you go in convinced that comets are always natural, you see a complex interplay of sunlight, rotation, and volatile chemistry painting strange but ultimately explainable shapes in space. If you are open to the possibility of technology, you see an object enter the system, fire something that looks like thrust, then reorient and coast, all while shedding engineered metal into its exhaust. Both stories can be told with the same data. That is what makes this moment so tense. For now, the spacecraft maneuver hypothesis remains just that, a hypothesis. It is a working story that lines up cleanly with a growing list of anomalies. It does not claim proof. It does, however, set the stage for a crucial test. If 3i Atlas really is under some kind of control, then the most decisive evidence may not be in the shape of its tail at all, but in something far more fundamental. Its path through space, and how that path changes as it swings around the Sunday. As the mystery around 3i Atlas deepened, the small club of people watching it turned into a global crowd of instruments. On any given night, there were backyard astronomers pointing modest telescopes at a faint smudge near the sun, while some of the most powerful observatories on Earth and in orbit bent their casts, schedules to catch a glimpse. The object was no longer just a curiosity in a survey image. It had become a priority target, and a quiet race began to see who could extract the most information from each photon it reflected. The Nordic Optical Telescope in the Canary Islands was among the first to show the strange geometry of the anti-tail in crisp detail. Its long exposure images revealed the forward plume like a ghostly spear, anchored to a point of light that was rapidly brightening. Far to the south, the Gemini South Telescope in Chile offered another angle. With its wide mirror and razor-sharp vision, Gemini traced the faint outer structures of the coma and tail, showing subtle jets and arcs that hinted at complex processes on the surface. Each new observation added another piece to a puzzle that refused to settle. Then there was the eye on Mars. High above the red planet, a spacecraft already in orbit carried a camera built for something else entirely. The high-resolution imaging science experiment, usually shortened to HiRISE, was designed to study Martian landscapes down to the scale of boulders and tracks. When mission planners realized that 3I Atlas would pass within about 12 million miles of Mars, they seized a rare chance. They pointed the camera away from the ground and out into the black, aiming at a moving target from another star. If the observations worked as planned, those frames would contain the sharpest images of an interstellar object ever taken. Even at that distance, HiRISE can resolve details far finer than telescopes on Earth. The shape of the nucleus, the distribution of bright spots, the structure of jets blasting away from the surface, all of that might be etched into those pixels. For the first time, humanity might see an interstellar visitor not as a streaked blur but as a world, however small, with recognizable features. And then everything jammed. Back on Earth, a government shutdown froze routine operations across multiple agencies. Public release of new spacecraft images was not a matter of flipping a switch. It depended on people processing the data, checking it, packaging it, publishing it. Many of those people were temporarily not working. The data almost certainly existed, sitting on servers, backed up in archives, but the scientific community and the public could not see it. Just as the story of 3I Atlas hit one of its most critical points, the clearest views were locked behind a wall of bureaucracy. While those unseen images waited, another group stepped into the spotlight. The International Asteroid Warning Network, a coalition of national space agencies and observatories that usually focuses on impact threats, published an update. They had decided to add 3I Atlas to their official list of objects to be monitored. Not because it was on course to hit Earth, it is not, but because it offered a rare and valuable chance to stress test their global observing system. This was a long-duration target visible from multiple hemispheres with enormous scientific interest. In their careful, institutional language, they called it an excellent opportunity. Behind those dry words lay something more electric. When a network built to coordinate planetary defense turns its attention to a visitor, even one that is harmless, it means resources and attention are being mobilized on a serious scale. Observation campaigns were planned months into the future. Telescope time was blocked out on mountaintops and in deserts. Software pipelines that usually track near-Earth asteroids were tuned to handle a hyperbolic outsider. Scientists who spend their lives worrying about rocks that might kill us shifted, at least partly, to watching a rock that might teach us. Up in space, other machines were being nudged as well. Solar observatories like the Solar and Heliospheric Observatory and the Solar Orbiter, whose main job is to stare at the Sun, were asked to keep an eye on the region where 3I Atlas would swing through Perihelion. Their cameras are not optimized for comets, but they are in the perfect place to catch any dramatic outburst or fragmentation event near closest approach. Instruments on the way to Jupiter were told to grab a quick look if the geometry allowed. Every vantage point counted. For the small community at the center of this effort, the contrast was surreal. On one side, a sprawling global network of telescopes and spacecraft quietly realigned to study a single object from another star system in unprecedented detail. On the other, the most tantalizing pictures of that object yet taken were effectively stuck in a filing cabinet marked, "Do not process until further notice." The entire situation acted like a stress test of our civilization. Even if the universe handed us a clear image of an interstellar visitor, would we be able to see it, or would our own administrative systems get in the way? That tension between capability and fragility adds another layer of drama to the story. We have built tools that can catch a Manhattan-sized relic from a dead star system as it slips through our sky. We can coordinate observatories across continents and planets. Yet the flow of information can still be throttled by arguments over budgets and procedures. Somewhere in that gap, the sharpest view yet of 3I Atlas waits unseen, while the object itself barrels toward the sun and the clock on this natural experiment keeps ticking. To see how strange this object really is, you have to compare it to the kind of comets astronomers know well. A typical comet is a dirty snowball. It spends most of its life in the deep freeze far from the sunday. Out there, everything is quiet. Water ice, carbon dioxide ice, carbon monoxide ice. All of it is locked in a rock and dust matrix at temperatures just above absolute zero. Only when the comet falls inward does the show begin. As it approaches the sun, the first ices to wake up are the most volatile. Carbon monoxide and carbon dioxide can start to sublimate even 3 or 4 times farther out than Earth. They leak out through cracks, carrying dust grains into space, forming a faint coma and a modest tail. Water ice is different. It is stubborn. It usually does not erupt with force until the comet is inside roughly Earth distance from the Sunday. That is when familiar comets suddenly bloom, their tails stretching millions of kilometers across the sky. At around 1.5 astronomical units, which is roughly 1.5 times the Earth-Sun distance, a normal comet would be moderately active. You would expect some gas outflow driven by carbon dioxide and maybe a growing contribution from water, but nothing extreme. Comets that go wild at these distances are rare. Most of them save their most dramatic outbursts for later, when solar heating is much stronger. 3I Atlas did not get that memo. Even when it was well beyond Earth distance, it was already spewing water at rates of around 40 kilograms per second. Imagine a high-pressure fire hose aimed into space, and you have roughly the right mental picture. That kind of water production is usually reserved for comets that are much closer in. Yet this interstellar visitor was doing it in the supposedly quiet zone. At the same time, measurements showed that its overall composition was dominated by carbon dioxide in a ratio of about 8:1 compared to water. That 8:1 ratio is wildly skewed compared to most comets in our solar system, where water is the main player and carbon dioxide is a supporting character. The implication is that 3I Atlas formed in an environment where carbon dioxide ice was far easier to build up than water ice. Perhaps it condensed in a colder part of its birth system, or in a molecular cloud where the chemistry favored carbon-based ices. Whatever the case, it carries a chemical accent that does not match the typical comets we grew up with. Then there is the cyanide. Many comets contain cyanide-bearing molecules, and their breakdown products can be seen in spectroscopic observations. For 3I Atlas, the cyanide signal is unusually strong. Its coma glows with bright emission lines that say this object is rich in chemistry that is associated both with prebiotic processes and with certain high-energy reactions. Alone, that would simply make it an interesting laboratory for astrobiology. Combined with everything else, it becomes another weird spike on a chart that is already crowded with weird spikes. Behaviorally, 3I Atlas is also an oddball. It turned on early, becoming active at roughly 3 astronomical units, around 3 times farther from the Sun than Earth. Its jets and plumes are not evenly distributed. Images show structured features in the coma, as if specific regions on the surface are venting more strongly than others. That is normal. But the pattern of activity and brightness variation does not line up well with the simple picture of a lumpy, spinning ice ball. The light curve refuses to settle into the tidy rhythm you would expect from an object that is just rotating under solar heating. Add to this its apparent toughness. For an object that has wandered the galaxy for up to 10 billion years, 3I Atlas is remarkably intact. Interstellar space is not gentle. Cosmic rays, micrometeorite impacts, and thermal cycling slowly chew away at surfaces. Many models suggest that comets this old should be fragile, prone to cracking or fragmenting when they finally encounter strong starlight again. Yet so far, 3I Atlas shows no obvious signs of breaking apart, even as its activity ramps up and it plows deeper into the Sun's gravity well. Every one of these anomalies could be explained away on its own. Early activation might be due to an unusually porous surface or a deep reservoir of carbon dioxide that vents efficiently. Strong cyanide lines could be a fluke of composition in its birth cloud. A skewed carbon dioxide to water ratio might simply reflect a weird region of a long-vanished protoplanetary disk. Structural toughness could mean that most of the damage over billions of years happens deeper inside, out of view. The problem is not any single data point. The problem is the pattern. You have an interstellar object older than our solar system that turns on too early, spews water where water should be quiet, is dominated by carbon dioxide in a way most comets are not, glows with cyanide, throws a forward plume rich in an apparently engineered nickel alloy, then calmly flips to a standard tail as if something changed mode. Each time you try to tuck one anomaly into a corner with a clever natural mechanism, another anomaly steps forward and asks to be explained. Science has a guiding instinct called the preference for simpler explanations. If you find yourself stacking one unlikely condition on top of another to keep a familiar story alive, you are supposed to stop and ask whether a different story might actually be simpler. With 3i Atlas, the default story is that it is just a comet, albeit a very strange one. The alternative is that it is a device, wrapped in comet-like material, behaving under a blend of natural forces and controlled actions. Neither story is comfortable. Both demand that we extend our thinking, but one of them requires fewer contortions to match what we see. 3i Atlas is not our first interstellar guest, which is precisely why it is so unnerving. If this were a one-off, you could shrug and say the universe occasionally throws up a real oddball. But in the last 8 years, we have seen 3 objects from beyond the sun, and each one has broken our expectations in a different way. The pattern is starting to look less like coincidence and more like a message about how messy the galaxy really is. The first visitor arrived in 2017. Astronomers at the Pan-STARRS survey in Hawaii spotted a streak of light slicing through the inner solar system at a steep angle. Its path was hyperbolic. Its speed was too high to be bound to the Sunday. They named it Oumuamua, a Hawaiian word often translated as scout. At first, everyone assumed it was a small comet or asteroid that had been flung out of some distant system and had wandered into ours by chance. Then the numbers started misbehaving. As Oumuamua moved away from the sun, it began to accelerate slightly more than gravity alone could explain. Comets can do that when jets of gas act like tiny thrusters, but there was a problem. There was no visible outgassing, no coma, no tail, nothing obvious to push on it. To make the models work, you had to imagine it venting something very light and hard to see, like hydrogen, in just the right way. It was possible, but it felt strained. Oumuamua came and went, too quickly for us to get a clear picture. It left behind a nagging sense that something about our ideas of interstellar debris was incomplete. 2 years later, in 2019, another hyperbolic object appeared. This one was brighter and more obviously active. It sprouted a classic tail and coma that looked reassuringly familiar. It was named Borisov, after the amateur astronomer who first reported it. For many scientists, Borisov was a relief. Its composition and behavior lined up reasonably well with known comets from our own Oort cloud, give or take some quirks like a high carbon monoxide content. It was the cosmic equivalent of a normal guest who reassures you that the last visitor was just a weirdo. If the story had stopped there, most people would have filed Oumuamua under unsolved mysteries and moved on. Then 3i Atlas showed up, older than both Oumuamua and Borisov by billions of years, richer in carbon dioxide than most local comets, turning on early, throwing a forward plume laced with unconventional metal, then flipping to a regular tail in a way that looks uncomfortably like a maneuver. Taken alone, it would already be an extreme outlier. Taken as the third point in a 3-point pattern, it becomes something else. Ask yourself what it means statistically when you turn on all sky survey telescopes for less than a decade, and in that tiny slice of galactic time, you catch 3 interstellar objects. One accelerates mysteriously without a visible tail. One behaves like a comfortingly normal comet. One acts like a hybrid of comet and craft, with a trail of engineered metal in its wake. The safe conclusion is that we are seeing only the tip of a vast and varied iceberg of objects passing through the solar system all the time. Most of them are invisible to us. They are too small, too dark, too fast, or on trajectories that never put them in the narrow cones of sky our instruments monitor. The 3 we have caught are the bright, convenient ones, the ones that happen to cross our field of view when our technology was finally good enough to notice. If those 3 are already such a bizarre trio, imagine what the unseen population must be like. There could be thousands, tens of thousands, even millions of interstellar wanderers drifting through the outskirts of our system every year. Some would be plain chunks of rock and ice ejected from infant star systems long ago. Others might be chemically exotic, carrying the fingerprints of environments we have never witnessed. And a tiny fraction, if the technosignature hypothesis is right at all, might be artificial probes, built by civilizations that rose and fell before our planet had cooled. In that picture, 3i Atlas is no longer a lone oddity. It is one data point in a much larger story about how the galaxy populates space between stars. This perspective also turns the question around. Instead of asking why 3i Atlas is so strange, we might ask why we ever expected interstellar debris to be simple. Our intuition was built on a sample of one solar system. We looked at our own comets and asteroids and assumed that anything arriving from outside would resemble them. The last 8 years have rudely corrected that assumption. Oumuamua, Borisov, and 3i Atlas form a trilogy that tears up the idea of a standard interstellar rock. For scientists, this is thrilling and intimidating. It means that every new interstellar object we catch will likely bring surprises. For the rest of us, it carries a more personal message. The space between stars is not empty. It is alive with travelers, fossils, and possibly artifacts drifting on slow arcs through the dark. Our solar system is not an isolated island. It sits on a galactic highway, and we have only just begun to notice the traffic. If 3i Atlas was simply the third in a line of weird but clearly natural visitors, this would already be enough to rewrite entire chapters of planetary science. The fact that it is the one whose behavior most closely mimics purposeful motion makes it more than an academic curiosity. It asks a question that hangs over the entire trilogy. Among the countless objects slipping through our sky unseen, how many are just frozen rubble, and how many might be something more? For most of the 20th century, when people imagined contact with another civilization, they pictured a radio ping in the headphones of a lonely astronomer. The search for extraterrestrial intelligence tuned giant dishes to distant stars, hoping for a clear, mathematical signal that would cut through the noise and announce we are here. That vision has not panned out yet. The sky has been mostly quiet, but in the last few years, a new idea has taken root. Maybe the first evidence of another technology will not be in our ears at all. Maybe it will be in our telescopes. Scientists use the word technosignature for any physical clue that technology exists somewhere beyond Earth. A radio beacon is one kind of technosignature, so is the waste heat of vast energy. Collectors, strange patterns of light from a megastructure, or a chemical signature in a planet's atmosphere that screams industry. And then there are artifacts, actual objects that cross the gulf between stars. Probes, machines, things that might be drifting through our own solar system right now, disguised as natural debris. If you were designing a probe to cross interstellar distances, loudly broadcasting radio signals might be the last thing you would do. It takes power. It advertises your presence to anyone who might be listening, friendly or not. A more conservative strategy is to keep quiet, lurk in the background, and let the physics of space do most of the work. In that scenario, you build something that looks from a distance exactly like a rock or an icy body. It soaks up starlight, coasts along gravitational paths, and only occasionally uses its own engines to adjust course. From this perspective, 3i Atlas starts to look like a test case for a new way of doing the search for intelligence. Instead of asking whether someone is beaming a message at us, we ask whether any objects in our sky behave more like controlled vehicles than like passive rubble. We look for anomalies in trajectories, in exhaust, in composition. In other words, we look for technosignatures, not in the radio spectrum, but in the dance of rocks and comets around the Sunday. Consider what such a probe would need to do. It must survive for millions or billions of years in deep space. That means minimal moving parts, robust materials, and a design that can go dormant for long stretches. It must be able to navigate without constant guidance, following simple rules like steer toward planets with atmospheres or toward stars with promising spectra. It must be able to change its speed and direction enough to dip into interesting systems, then leave again. And it must be hard to distinguish from the natural clutter that fills every stellar neighborhood. Wrap that machine in a thick shell of rock and ice and dust, and from the outside, it becomes almost indistinguishable from an ordinary comet. Its hull can be an engineered alloy that resists radiation and thermal stress. Its internal systems can be shielded by meters of frozen carbon dioxide and water. When it needs to brake or adjust course, it can vent gas through nozzles or fractures, sending out plumes that look, to our instruments, like jets from sublimating ice. Seen from far away, the whole thing is just another dirty snowball waking up in the light of a star. The unsettling thing about 3i Atlas is how well it fits pieces of that picture. It is wrapped in volatile ices, yet laced with a nickel-rich metal that looks engineered. It was quiet for eons, then lit up as it fell toward a new star. It produced a forward plume that mimics braking thrust, then switched to a trailing tail. Its activity pattern and light curve resist simple natural models. None of this proves anything. Nature is creative. But if someone had handed you this behavior as a design goal for a stealthy interstellar probe, you would nod and say, yes, that would work. This is where the emotional weight of the story shifts. If 3i Atlas is a probe, it is almost certainly not one aimed at us personally. Remember its age, 7 to 10 billion years. The civilization that might have built it could have vanished before the Earth even formed. Whatever instructions it carries, whatever logic guides its movement, would be the frozen echo of decisions made in a very different galaxy long ago. We would not be talking to living aliens. We would be examining a message in a bottle that has been drifting in the cosmic ocean since before our sky had familiar constellations. First contact in that sense would not be a conversation. There would be no mutual greeting, no exchange of ideas. There would be recognition. On one side, a young species finally capable of reading subtle clues in light and motion. On the other, a machine that simply does what it was built to do, indifferent to whether anyone is watching. It would be contact across time, not just space. A quiet acknowledgement that technology has arisen at least twice in the history of the galaxy. Not everyone is ready to entertain that possibility. Many scientists are understandably wary of invoking aliens when every anomaly still has at least a theoretical natural explanation. They warn against seeing intent where there is only physics, against turning every strange comet into a potential spaceship. They insist that extraordinary claims demand extraordinary evidence, not just suggestive patterns. They are right. That standard is what keeps science grounded. And yet, the idea that technosignatures could appear as disguised probes has moved from fringe speculation into the edges of mainstream research. Papers in serious journals now explore how to distinguish natural interstellar objects from potential artifacts using only trajectories and light. Committees talk about how to respond if such a candidate is found. 3i Atlas sits at the intersection of those conversations. Whether it is ultimately judged natural or artificial, it is forcing us to sharpen our tools for telling the difference. In that sense, the quiet version of First Contact may begin not with a definitive announcement, but with a question we cannot easily close. We look at the data, we run the models, and at the end, we may find ourselves saying not, we have met another mind, but we can no longer rule that possibility out. For a species that has spent centuries wondering if it is alone, even that uncertainty is seismic. It changes how we look at every new object that wanders in from the dark. There is a point in every good thriller where the lights go out. For 3i Atlas, that blackout is built into the geometry of the solar system. Very soon, it will reach Perihelion, the closest point to the sun on its hyperbolic path. Then, for weeks, it will pass behind the blinding glare from our point of view. Telescopes that have been tracking it night after night will suddenly lose it. The cameras will keep rolling, but all they will see is the raging face of the Sunday. Before that happens, astronomers are in a frenzy to grab every possible measurement. On the inbound leg, they are tracking brightness with ridiculous precision, watching for subtle flickers that might betray rotation, jet activity, or structural changes. They are mapping the tail and coma, looking at how their shapes respond to increasing solar heat. Spectrographs are trained on the object to see whether the mix of gases changes as it dives deeper into the sun's light, especially around the distance where water-driven activity should explode. Every data point becomes a before picture. Solar observatories take over at the moment of closest approach. Instruments like the coronagraphs on the Solar and Heliospheric Observatory and the Solar Orbiter were mainly built to study eruptions on the Sun, but they are also surprisingly good at catching comets that skim through the inner solar atmosphere. For a brief window, as 3i Atlas threads its way near the Sun, these cameras may catch a faint streak or a blossoming halo cutting across their field. The resolution will not be pretty, but the timing will be priceless. During this time, several possible storylines are in play. One is the spectacular disintegration. Many comets do not survive their brush with intense solar radiation. They shed layers, fragment into clouds of rubble, or blow themselves apart in dramatic outbursts. If 3I Atlas is fragile, the coronagraphs might record a sudden flare of brightness followed by a messy spray of debris. When the object emerges from behind the Sun weeks later, it could be a ragged cluster of fragments instead of a single nucleus. Another storyline is the quiet passage. The object swings around the Sun, heats up, vents more gas, grows a longer tail, but remains structurally intact. When it reappears in the morning sky, it looks bigger and brighter, but still clearly a single body, now heading back out into deep space. That behavior would be more consistent with a tough, compact nucleus wrapped in a thick layer of volatile ices, exactly what you might expect from an interstellar wanderer or from a well-protected machine. The most intriguing storyline, however, is the one that plays out not in a photograph but in the math of its orbit. Long before Perihelion, teams around the world have been using successive positions of 3I Atlas to refine its trajectory. They plug those positions into models that include the gravity of the Sun and planets and the gentle push of solar radiation. They even include estimates of how asymmetric outgassing can act like a continuous low-thrust engine, nudging the object's path. From all of this, they compute where it should be after it swings around the Sunday. Once the blackout ends, and telescopes lock onto 3I Atlas again, the first order of business will be to compare prediction and reality. If the object appears exactly where and when the models say it should, within the usual small error bars, that is strong evidence that only known forces have acted on it. Gravity, sunlight, and gas jets will have done their work, but nothing more exotic. If, however, there is a significant mismatch, if it is ahead of schedule or behind, or off to one side by more than the models can reasonably accommodate, then something else will need to be added to the equation. Non-gravitational accelerations are not mysterious by themselves. We have seen them in comets whose jets are particularly strong or lopsided. What makes 3I Atlas special is that it already appears to have shown behavior consistent with a controlled braking phase. If the post-perihelion trajectory demands an extra push that does not match any reasonable outgassing pattern, the case for some form of active maneuvering gets much stronger. An unexplained deviation would not be a smoking gun, but it would be the kind of clue that forces even the most cautious astronomers to pay attention. There are other signs the teams will watch for during the return. Has the tail changed in a way that cannot be tied to solar activity alone? Are there new jets from unexpected regions of the surface? Has the rotation state altered in a way that suggests internal mass shifting or deliberate reorientation? Does the rate of fading as it recedes match what we would expect from a natural comet, or does it show odd plateaus and bumps that could hint at intermittent propulsion? Each of these is a subtle test, but taken together, they form a kind of interrogation. The strange part is that all of this will happen while most of the world goes about its normal routines. Somewhere above the dawn horizon, a point of light will rise that carries within its path answers to questions humans have asked for generations. Are we alone? Is anyone else building machines out there? Can artifacts cross the immeasurable gulfs between stars and endure long enough to be noticed? The universe is about to mark a box on that silent questionnaire. Scientists have set up their instruments to catch the response. The rest of us are left in the dark with a simple invitation. Wait, watch, and be ready to live with whatever answer comes back. When the data finally come in after perihelion, they will tug the story in one of two broad directions. In one version, the trajectory lines up with the models. The brightness evolution looks like an overachieving comet, and the odd composition can be squeezed into updated theories of interstellar ice. In the other version, the path is wrong in a way that cannot be shrugged off. The activity pattern refuses to behave like simple sublimation, and the list of coincidences grows too long for comfort. Both endings are profound. Neither leaves our view of the universe untouched. Start with the quiet outcome. Imagine that every careful measurement says the same thing. 3I Atlas is natural. It is wildly exotic compared to the comets of our own system, yes, but still the product of gravity, chemistry, and time, with no guiding hand. That result would not be a disappointment. It would be a revelation that our earlier picture of comets was parochial. We would have hard evidence that planetary systems across the galaxy brew ices and rocks in far stranger recipes than we imagined. In that case, The forward plume and the nickel-rich alloy and the skewed gases would become clues to an alien birthplace rather than to alien engineers. We would be able to say that somewhere billions of years ago, in a region of the Milky Way that may no longer exist, conditions favored carbon dioxide over water, piled cyanide into ice, and forged metal mixtures that have never cooled inside any planet we can sample. 3I Atlas would be a fossil from a vanished environment, a physical memory of a part of cosmic history we could never otherwise touch. Even in this purely natural reading, something important would shift in our story. Interstellar objects would no longer be rare novelties. They would be recognized as messengers from the broader galaxy, carrying direct samples of distant chemistry into our laboratory. Missions that today are only sketches on paper would gain urgency. Concepts to send spacecraft out to intercept future visitors, to take samples as they race through, would move up the priority list. An ancient comet that is not a ship would still be enough to change how we think about exploration. Now consider the harder outcome. The numbers refuse to sit still. The post-Perihelion track demands an extra push no outgassing can provide. The brightness curve shows plateaus and jumps that look more like engine cycles than like random flares. More detailed spectra confirm that the alloy in the plume really does match. Engineered metals, and no one can find a clean natural route to create it. In that world, the cautious language begins to crack. Papers that once spoke of possibilities start to talk about likelihoods. A phrase that was whispered in conference hallways begins to appear in formal abstracts: artificial origin. The emotional impact of that shift would be difficult to overstate. For generations, we have asked if we are alone with no real feedback. Suddenly, we would have a physical answer. Not a friendly broadcast, and not a landing craft, but a machine that proves someone else once walked the same technological path we are on now. Somewhere, sometime, beings that were not human burned metals, shaped alloys, and built a device sturdy enough to cross the galaxy and keep functioning long after their own sky changed beyond recognition. At first, fear would mix with wonder. Questions would explode that no one can fully answer. Did they send more than one? Are there others in the solar system? Right now, dormant in the dark. Could any of them still be active in a way that matters to us? Are we being watched, even if only by ancient autopilots obeying rules written eons ago? Governments would convene panels. Space agencies would scramble to design missions that could get closer. Ethicists and philosophers would dust off old thought experiments and realize they are now policy questions. Yet, as the shock settled, another feeling might rise: relief. Because if 3I Atlas is an artifact, it tells us that intelligence is not a freak accident confined to one small world. The universe has done this at least twice, and if it has done it twice, it may have done it many times. Intelligence might be as natural a product of cosmic evolution as stars and planets. Civilizations may flare and fade across the ages, but the universe does not forget them entirely. It keeps their machines in motion. It lets their probes fall into new skies, where new minds can find them. In that sense, we and whoever built 3I Atlas would be joined in a strange, asymmetric partnership. They sent something out. We noticed it. They could not have known we would exist by the time it arrived, any more than we can know who will find our first interstellar probes. But across billions of years, our stories would intersect for a moment around this one object, lit by a single star on the arm of a spiral galaxy. There is also a sobering lesson hidden in both outcomes. Whether 3I Atlas is comet or craft, it has survived journeys and timescales that dwarf anything our species has experienced. It reminds us how young we are, how brief our recorded history is against the clock of the cosmos. It also hints at how far we might go if we manage not to destroy ourselves, if we learn to build things that can carry our curiosity across deep time. In the end, the label we pin on this visitor may matter less than the shift it triggers in us. 3I Atlas has already forced astronomers to build better tools, to coordinate more tightly, to think more flexibly about what is possible. It has invited the rest of us to imagine that the space between stars is not empty, but full of stories in physical form, drifting at high speed past worlds that are just now learning to look up. Whatever the data finally say, this object has already changed our place in our own narrative. We are no longer a civilization that has never seen an interstellar traveler up close. We are a civilization that has watched one arrive behave in ways we do not completely understand, and pass on. The next time a hyperbolic visitor appears in our sky, we will meet it with sharper eyes and a deeper sense of what might be at stake. The universe has given us a mystery. How we respond to it will say as much about us as it does about whatever is rushing past the sun right now.